Thanks for joining us, everyone. We're going to give a few more minutes for folks to join the call, and then we'll go ahead and get started. All right. Good morning, everyone, and welcome to our 7th webinar in the Florida-Friendly Landscaping Green Stormwater Infrastructure Series. This webinar will be 1.5 hours long and will be recorded and available along with the rest of the series. Today, we will learn about design techniques, and we'll hear from experts from the University of Florida and Streamline Technology. Today's speakers include Dr. Eban Bean from the University of Florida and Pete Singhofen from Streamline Technologies. Additional information about design techniques can be found on our Green Stormwater Infrastructure Program website, a link to which will be dropped in the chat box. Next month, on September 21st, we'll have a webinar focused on municipal and regulatory considerations. At that webinar, attendees can expect to learn about how ordinances, BMAPs, BMP trains, and the new stormwater rule update relate to GSI practices. To see the full lineup of our webinars, including our recorded webinars, please visit floridafriendlylandscaping.com and follow the links to training and FFL webinars. A link to that will also be dropped in the chat box. This webinar has 1.5 credits for CEUs available for Florida Friendly Certified Professionals, FNGLA credits, floodplain managers, professional engineers, and landscape architects. The link for that will appear in the chat as well. And if you have any questions or issues related to your CEUs, please reach out to Claire Lewis, and her contact information will also be in the chat. A link to GSI funding information will be in the chat as well. And we have also recently launched our GSI inventory survey, which we use to collect information on GSI projects throughout the state. A link to that survey will be in the chat, and users can submit up to 3 projects per survey session. If you have any questions for today's speakers, please submit them in the question and answer box as opposed to the chat box. That way our moderators don't miss your questions. We'll have time after each presentation for some questions, as well as towards the end of the webinar. And if we end up running a little short on time, we'll just save question and answers until the end. With that, we'll turn things over to Dr. Eban Bean to get us started.
Thank you very much, Nathan. It's great to be back again. And today we're going to be talking about design techniques. But as sort of a precursor to that, lead up into my colleague Pete's presentation, I'm going to go over some of the regulatory background to kind of set up sort of why do we have to design, or where did these requirements come from, and how do they all link together? Okay, I'm going to start out just by recapping sort of some generalities or sort of some broader concepts that I'm going to go through kind of quick, because I think at this point, many of you probably are pretty familiar with these. And you may have seen them in a previous webinar a little bit as well. So when we increase the imperviousness that's on an area, we start to change or affect that water balance. And so here as we have here from the left to the right, we have sort of natural ground cover, no imperviousness. We have evapotranspiration might be 40%, infiltration might be 50%, and runoff is 10%. These are just conceptual starting points. And as we increase that imperviousness, we start to shift that overall water balance. And so we start to increase the amount of runoff, and we start to reduce the amount of infiltration and reduce the amount of evapotranspiration. And so the actual increase in water that's coming off the land, it may look like it only changes by maybe 20 or 45% between the natural ground cover and the medium and high imperviousness. But that's actually a 3 to 5.5 fold increase in the amount of water that's leaving the site And so there's a lot of aspects where that can affect the environment and the water quality. Not only that, but in our urban areas, there's lots of sources of pollutants that can get picked up with stormwater runoff. So for example, metals and PAHs can come from highways. We can have sediments accumulating on pavements and atmospheric deposition of organic debris. We have fertilizers that, if they're not applied properly, can either run off or potentially, in some cases, leach into the ground. And then our pets, as cute as they are essentially point sources of pollution that we need to make sure to pick up behind them. These are just sort of some examples of pollutants that are in the environment that runoff can pick up, and transport downstream into our water bodies. And historically, the approach to stormwater runoff was really just to manage flood control. The main idea being, let's get the water off site as quickly as possible. And so our approach has been to basically put that into either a canal, channel, or a pipe system, and then put that into the nearest waterway. That got the water off our site as quickly as possible. Now that becomes an issue when all of that water is coming to you, or maybe our pipe or conveyance system is not large enough, and we start to have the backup and water builds up at the surface and floods. Or we have an excess of nutrients or pollutants that are going into the water and starting to impact that water quality. So we can have algal blooms, which we've seen probably quite a bit, more than we'd like to in the news, as well as fish kills and even channel erosion that can occur. So I want to go back and kind of just give you a quick history lesson on where our stormwater rules or requirements actually come from. Like, where do these requirements that we design for or have to meet actually come from? Well, if we go back to 1969, there was sort of a critical event that happened. It wasn't really the only thing, but it was sort of the tipping point. And this was the Cuyahoga River fire. The river had caught fire many times actually before, but this one was particularly large, and it was an indication of how polluted the Cuyahoga River was. It was getting a lot of industrial pollution discharged into it. Sparks from the bridge that you see here on the left, where they were doing some welding, fell down and basically caught a lot of that pollution on fire. Well, this caught a lot of media attention and ultimately was the driver. It was not the only issue, but it was the driver who kind of precipitated the passage of the Federal Water Pollution Control Act, or what we refer to as Clean Water Act. This was sort of foundational for water quality standards and water quality efforts in the nation. So what this did was it prohibited any unpermitted pollutant discharges to surface waters. It also had some pretty ambitious goals of basically making all waters fishable and swimmable by 1983. Missed that just a little bit, still working towards that. And with the goal of eliminating all discharge of pollutants by 1985. So we kind of underestimated the size and magnitude of that issue. In fact, stormwater wasn't actually regulated until the 1990s as a part of this, and I'll touch on that in just a moment. But what the EPA does is it essentially delegates the Clean Water Act, the implementation of that law, to the different states, each individual state around the nation. And one of the main programs is through what's referred to as the National Pollutant Discharge Elimination System, or NPDES. This is one that I'll go into a little bit of depth here. So again, this was created under the Clean Water Act, Section 402. This initially focused on point sources of pollution. So anything that had basically a pipe that was discharging, and the focus was essentially on industrial pollution that was discharging into rivers and waterways, wastewater that was coming from a wastewater plant or just a sewage system that was going directly into waterways, and then any municipal discharges of water into our water bodies. And so if the question kind of came up, can I send my runoff into the stream as long as it doesn't hurt it, as long as it's not impacting the stream quality? And so at that point, stormwater wasn't really addressed as part of this, and there's a few reasons. So when we look at the definitions, this is the goal of the Clean Water Act and the elimination of the National Pollutant Discharge Elimination System focused on point sources. And so with a point source, this was basically anything that had to be discharged, any pollution that was discharged through a single point. And so this meant it had to be basically and have an outlet or a defined location. And so you can see sort of some of these aspects of or features that might define a point. So anything that's confined or discrete conveyance might be a pipe, ditch, channel, anything that conveys water, right? Whereas non-point source is any source that's not really legally defined as a point source. So which is urban stormwater runoff? Well, it's both actually, depending on where it comes into play. So as stormwater runoff begins at the lot level and comes off of, let's say, a rooftop, and then rolls off of the driveway and maybe into the street, that is non-point source. There's no actual point where all that runoff's coming from. It's coming from a large area, so it's a non-point source. However, when that water gets collected and enters into a stormwater collection system, that is now in a system that now has a designated out point, or basically a designated outlet. And so the discharge, a point source, it becomes a point source because it's now being discharged from that stormwater collection system as a point source. And all point sources are regulated under the NPDES program. So this was actually kind of went through a lawsuit for the NPDES program to actually cover stormwater discharge. And actually what we're dealing with is this led to the development of the MS4 program, which is another acronym in series here that stands for Municipal Separate Storm Sewer System. There are actually two phases of it. And the first phase dealt with larger municipalities. Second phase in the late 90s dealt with smaller municipalities. And so the definitions here kind of, or the terminology essentially defines what it applies to. So there is a responsible entity that is a city, county, or state, a municipal. Separate, in this case, it means that it is separate from sanitary sewers. So we have sewers that are just underground conduits that can be sanitary or storm sewers. And in this way, the term is referring to the storm sewers being separate from sanitary sewers. Storm, so we're only looking at the storm side, and then the system is a network of interconnected elements. So just kind of cover the definitions there. A few more sort of alphabet soup or acronyms here. Section 303D of the Clean Water Act defines the water quality standards or defines some criteria that deal with that. Essentially saying that states need to establish those by monitoring or assessing water bodies on a regular basis. This usually happens about every 5 years as a cycle. FDEP is responsible for that. And for waters that are not meeting those water quality standards, that list has to be submitted to the EPA. For the impaired waters to meet the water quality standards, the TMDLs, these are basically pollutant budgets, need to be developed so that they meet the water quality standards. So basically a pollutant diet, how much either nitrogen or sediment or whatever the pollutant is of concern has to be allocated to the different sources within that watershed. And then BMAP is the actual plan for how the actual projects that would be implemented to help achieve the water quality to meet the water quality standards. And so with that, MS4s or these stormwater systems are subject to managing pollutants that are coming through that stormwater system to comply with TMDLs and BMAPs, okay? And there is, part of that is dealing with the generic phase 2 MS4 permit renewal. So I mentioned briefly that there's two phases of the NPDES MS4 program. So phase 1 are the large and medium municipalities. This began in 1990. And so these are basically any municipalities that were 100,000 or more. So you think about, we had about 14 of those. I'm sorry, not 14. We had 14 elements in that permit. But each of these large municipalities had to obtain an individual NPDES permit. So they have some special unique requirements. It's tailored to their community. Whereas phase 2 went into place in 1999. And this is what is called a generic MS4 permit. And this is issued by FDEP. It has common criteria and control measures. And so it's a little more generic just for the smaller municipalities not to have to develop their own things. The permits have to basically be renewed every 5 years. And within that phase 2 permit, there is one of the aspects of that control measure is a stormwater management plan. And so that can have include in it additional stormwater requirements for new discharges and new construction. But NPDES basically applies to everything that is existing. So you've probably heard of ERP, which is the Environmental Resource Permitting Program, which also applies to stormwater. So how do these relate? So they are separate programs. Okay, so NPDES MS4 derives from our federal regulations, all the way from the Clean Water Act, EPA, FDEP, and so forth. New developments may have some requirements on their projects if they drain into a city's storm sewer system. The MS4 permit encourages the use of LID and Green Stormwater Infrastructure, and it can cover existing and new development draining into MS4, into the MS4 system. Now, the ERP program is a state level program that was actually developed before the NPDES MS4 program. It's unique to Florida, and it basically regulates any changes to surface water flows. And it's not just stormwater, it also does wetlands and dredging and dams and so forth. But it covers basically stormwater management systems or stormwater that discharges into Florida's waters. And could be for individual development projects or phases, but the implementation is delegated to the water management district, and so the requirements vary slightly by each water management district. And each one has these requirements for it in the applicant's handbook number 2, whereas applicant's handbook 1 is for statewide. Just to kind of wrap up with ERP. So this essentially, it addresses activities that involve altering those surface flows. A lot of times we hear about minimum flows and levels. This is also under the responsibility of the water management district. If we're increasing runoff, if we're generating runoff from upland construction, that's going to change the discharge or amount of water and the pollutants that are going into that water downstream. Each water management district has slightly different requirements. They are all currently technology-based, which is a presumptive criteria for meeting the water quality treatment. We'll talk a little bit more, I think, next time about the proposed changes to the ERP rules. But some examples here are that if you basically capture 1/2 inch of runoff or 1.5, or runoff from 1.25 inches of rainfall from the impervious area, and then infiltrate that in the 72 hours, then you have met the presumption of protecting water quality. Okay. The water management districts also have requirements for flood control as well, whereas NPDES and MS4 tend to be more on the pollutant loading and tying into the BMAPs and TMDLs and so forth. But local municipalities may have additional requirements for their storm system or their stormwater management plan that developers or permits may have to meet, or in addition to the ERP permit. With each of these, whether it's local or ERP or any other stormwater side of things, there's a requirement to demonstrate that you're meeting those permit requirements to receive the permit and be allowed to go forth with the modifications of the site to develop it from whatever its current state is into a developed land. And this is going to be oftentimes utilizing accepted models and methods for analyses. So one of the most common, if not the most common model used in stormwater management in Florida is what Pete's going to kind of introduce us a little bit to, is ICPR. It's been around for a long time. And one of the great things about it is that it handles the interconnectedness between surface and groundwater very well. And that's one of the aspects that has to be kind of accounted for and incorporated into a design of a system based off of the soils, the geotechnical depth of the water table, and how, if you're doing infiltration, how that's going to interact with that water table. And then the demonstration, there's a variety of storm events, but it's primarily those storm events are for meeting the flood requirements. So I've kind of gone through this pretty quickly. I probably went a little bit longer than I intended, but just wanted to give you sort of a heads up about some change or some, heads up about some of the requirements or where some of our stormwater requirements come from in the state. So we have the NPDES that basically is derived from the federal level, but we also have our own state program that helps to protect our waters and uses a different system. But both of those have to be achieved and met. So with that, I think I'll just go ahead and turn it over to Pete if he wants to go ahead and take it away. Pete, still muted? And
yeah, I was trying. I think I got it now.
All right, sounds good.
Having some technical difficulties finding the unmute button. They got moved on me. But thank you, Evan. I appreciate it. And thank you, everybody, for taking an hour and a half out of your day to listen to us. And yeah, I'll be getting some Teams notices. Let me kill that.
Hey Pete, just want to let you know we can't see your video right now if you wanted to turn that on.
You can't see me sharing the screen or just myself?
Can't see you.
Yeah, just
okay.
yourself.
Yeah,
there you go. Perfect.
Yeah, okay. So what I want to talk about is modeling stormwater treatment systems, and that kind of falls into the design mode of these things, and I want to focus a lot on the pollutant load aspect of it. So the topics I want to cover are the water quality module design strategy that we're using in ICPR. And then I want to go over how you can use this tool to screen BMPs. Let's say you have a small city or that you're considering implementing a strategy. We can look at different types of BMPs and evaluate kind of generally how they would perform. Then I want to get into the weeds quite a bit with a roadway retrofit project where we're going from gray to green. This was an existing roadway. It was a 4-lane roadway with not a lot of traffic to it, and so the city of Auburndale wanted to change that to a 2-lane and then implement quite a few green stormwater infrastructure features into it. So in that, we'll talk about rain gardens, bioswales, pervious parking with underground storage. We'll look at those individually, and then we'll start putting the pieces together. And I believe we have about 50 different BMPs that are interconnected together. And then we'll look at the cumulative removal efficiencies in this system. And naturally, we won't forget about the hydraulics. We'll look at those as well as the pollutant loads. And then another thing that I'd like to talk about are interconnected wet detention ponds and some of the considerations of that. When you start connecting wet ponds together, you have different removal efficiencies for each one. What happens when they're connected together? How do you, what type of adjustments do you need to make in the calculations? And then we'll just kind of summarize it at the end. Let's see. Let's see. Okay, so on the water quality module design strategy, we wanted to take a watershed approach. We didn't want to just look at one BMP or 2 or 3 that are kind of somehow combined together. We wanted to look at entire watersheds if possible. And so the water quality is fully integrated with the hydrology and hydraulics. We've combined them together. When we run the hydrology and run the hydraulics, we can simultaneously run the water quality. It is based on event mean concentrations, and it's applied to distributed hydrology. And I'll get into that in more detail in just a little bit. We do a mass balance at the nodes. The pollutants are then transferred via links or connections between the nodes, and removal efficiencies can be specified at any basin, any node, or any link. And then percolation and also 2D groundwater can be used to remove the pollutants. You have to perform a continuous simulation rather than just a single storm event like a 100-year event. You have to run a long-term continuous simulation. And we can analyze multiple constituents simultaneously. So if you want to look at TP, TN, and total suspended solids, you can look at those all at the same time as you're doing the hydrology and hydraulics. We've also built in initial constituent concentrations, irreducible concentrations, and also making adjustments for boundary conditions and water quality at the boundaries. So we're working with the physical processes of infiltration and percolation and also evapotranspiration. They're actually modeled rather than relying on empirically based performance curves. In other words, we're not making assumptions that that a dry pond will always recover in 3 days. It might recover in 6 hours in the dry season, but in the wet season, it might take it 2 weeks to recover. All of that is built into the calculations. And so in this table on the left, we have different ICPR functionality. And then on the right, we have the different types of BMPs that can be modeled or incorporated into the system using the associated ICPR functionality. For example, we have percolation links and French drain links in ICPR. With those, we can model dry retention, exfiltration trenches, underground storage, treatment swales, pervious pavement, rain gardens. We can specify removal efficiencies at nodes. We would do that for like wet detention systems, managed aquatic plant systems, user-defined BMPs, and so on. We can set up the removal efficiency at links. We can also address pollutant removals with storage considerations, evapotranspiration, and irrigation. So I'll show you just a couple of the data forms for those of you who are somewhat familiar with ICPR will recognize some of these drop-down menus. But these are new data forms that we're adding. So under tables, we'll have a water quality option there, and then we can set up the EMC constituent sets. And you can have multiple constituent sets. You can do sensitivity analysis. But once you set up a set, you click the constituent tab, and then a table comes up, and this is where you can load in a particular constituent like total nitrogen. You can set up irreducible concentrations, default concentrations, and then there's a table down below with land cover zone, and then the corresponding event mean concentrations over on the right side in milligrams per liter. And then you click on the next one and you would do the same thing for that, and so on. Now you might look at this and say that would be horrible if we had to type that in every time. We have a CSV file that you can import, and it just kind of fills these up in a couple seconds. And then in the simulation manager, under the resources and lookup table tab, one of the lookup tables will be EMC constituent set. And if you right click on that, you can then select which table you want to work with. This is how we invoke the water quality computations here. If we leave that blank, it will just do strictly the hydrology and hydraulics. But as soon as we add this table to it, it then triggers water quality in addition to the H&H. So here's an example of just a catchment area basin that has multiple land use types within it. So the hydrology is distributed. And we have tools in ICPR where we can intersect a basin or catchment map layer with soils and with land use to form subpolygons. So in this case, we have a transportation land use zone. We have high density residential. We have a commercial area. And then we have water features, stormwater ponds that are in the system. And this is one catchment area inside of a much larger watershed. So if we break this down, the way we might do this traditionally is we have the different land use categories. We have the surface area of each of those categories. We would estimate a runoff coefficient from those. And then given the concentration for, say, total nitrogen, we would multiply these out along with an annual rainfall to get an average annual pollutant load. Well, with ICPR, instead of doing a runoff coefficient, we use the green amp method instead of the runoff coefficient. And by doing a continuous simulation, we can track the soil moisture conditions continuously throughout the simulation. And what we end up with is something like this. This is a 20-year simulation, and the average annual total nitrogen is about 1,400 pounds, and the total phosphorus is about 260 pounds. And we can get a breakdown by month of each of those, and then we can, from there, calculate the average annual loads. So now let me move into how we can use ICPR to screen BMPs. This is the town of Auburndale, and it drains into 3 different lakes. One here on the west side, one on the north side, and then a smaller remnant sinkhole. And so let's say that we're just contemplating using different types of BMPs in the city, and we want to get some sense for how effective they would be. So we can break these up into different zones. And this one here is a commercial that we intend to use pervious pavers on. And we're going to estimate that we can get 2 inches of retention in that particular zone. And then we have medium density residential, and we're going to assume we can get 1 inch of retention there, and so on. Rain gardens over here, maybe the water table's up higher, the soils aren't as good, and we'll use rain gardens with 1/2 an inch of retention, and so on. So we go through that, we set that map up, we intersect it with the different catchment areas, and then in the impervious lookup table, we can set initial abstraction for the impervious areas and also for the pervious areas. And so for commercial with pervious paver type 1, we're assuming that the first 2 inches of rainfall will get trapped in these systems and percolate or evaporate. The commercial pervious pavers type 2, we get 1 inch of initial abstraction, and so on for each of these zones. Then we, in the simulation manager, we can set an initial abstraction recovery time. Just for example, if we follow the 3-day rule that your recovery for these PERC type systems has to be evacuated over a 3-day period, we can set the initial abstraction recovery period to 72 hours. So what I did is I ran it through saying, okay, what if we get 24 hours? We have really good soils and we can recover in 24 hours versus 48 hours or 72 hours. The runoff volume reductions are decrease with the longer it takes to recover the storage in these treatment systems. So for example, the areas draining to Lake Lena here, if we can get 24-hour recovery on them, then we would have 68% removal of the volume. That's what would go back into the groundwater table, and that would be our removal efficiency. If we can't recover that quick and it goes to 48 hours, the removal efficiency drops down to 63%, and then a 72-hour recovery would drop down to 59%. And then we've broken it up to the different lakes, and then we looked at the combined effect for this system, and we vary from 68% removal down to 60% removal. So that gives us an idea of how these would work. Once we have that done, we can then start working in the details and nail this down a lot more precisely. Which leads me to our first case study. And this is in Auburndale, and this is referred to as PK Avenue. And it was a 4-lane road, and the city wanted to add some BMPs, green infrastructure, to it and make it a much more pleasant pedestrian area, but also improve the water quality going to those lakes. So I want to thank the city of Auburndale, and especially thank Chastain Skillman. This was their project. They provided me with these beautiful photographs, but also the construction plans and a lot of other data so that I could use this as a demonstration. And then a special thanks to Drew Morrison, who is with Chastain Skillman, and Kevin Albrecht, who used to be with Chastain Skillman. He's on his own now, but I've worked with both Drew and Kevin, and I got a lot of great data from them. And these photographs that I'm showing in here are all courtesy of Chastain Skillman. So let's start with one of the rain gardens. It looks like this on the right, where we have a whole series of these that are connected in different ways. They planted some native vegetation around it. They put some stone in the bottom of it. But this has 2 inlets to it from the street. So the water will run down the curb and gutter and then drop in to the system. And then if it fills up, as it's running off the street into the bottom, it's going to be perking out. But if the rain intensity is very high, it can then fill up and pop off and then go into a storm sewer system. So the way we would model this in ICPR is we would set up a catchment area, and we call that a basin. We would place a node in the rain garden itself, and that node would have a stage versus wetted surface area relationship. In other words, it's accounting for the storage in the rain garden. We would have, with the catchment, we would treat that as a manual basin, and we would intersect that with different land cover zones, different soil zones, and so forth, and get a breakdown of that so that we have the distributed hydrology associated with this catchment. The runoff from that gets assigned to the rain garden. We add a perk link to it, a percolation link, and that's how we can account for the water infiltrating into the ground. And then if the water level gets up high enough, it would pop off a weir and connect up to the storm sewer system. Now we're ignoring the storm sewer system for now, because I just wanted to keep this simple and show you how something like this would work on a single catchment area, a single BMP. So in the manual basin data form, we have tools that automatically intersect the basin map layer, the land use and the soils and so forth. But we get a breakdown of, think of these as sub-basins or sub-polygons. We have the area of each of those intersections. we have the corresponding land cover for those. We have the soil zones. These all happen to be the same soil type. We have a rainfall name, and this is tied into a NexRad grid. We use NexRad data to run the long-term simulations. And then we can set up a crop coefficient zone. This is for evapotranspiration purposes. And then we have a reference evapotranspiration station, which happens to fall on the same NexRad grid. So with the land cover zones, we have a corresponding impervious percentage table, and we have an EMC table. This is where we can figure out what the pollutant loads are going to be for each subpolygon. For the soil zone, we have a green amp lookup table that ties into these numbers here. And these we get from the NRCS Web Soil Survey, and this is called the MU-key, which is a unique identifier for the various soil types. The rainfall name is tied into a NexRad rainfall file. The crop coefficient or the crop coefficient zones are tied into a crop coefficient table. And the reference ET is tied into a reference ET resource file, which is based on some USGS data that's available for the state of Florida. The total area is about a quarter acre, about 0.24 acres, pretty small, 10,000 square feet. If we look at the node data, we can develop from the stage area table, we can develop a stage or elevation versus storage curve. And from that, we know that the overflow is at elevation 160.8. And from this relationship, we can determine that there's 384 cubic feet of storage up to the overflow, which happens to be about 0.44 inches of runoff. So from there, we set up the PERC link, and I won't go into all the details on this, but it has the aquifer base, the water table elevation, and that could be the seasonal high water table, conductivities, fillable porosities, and so forth. And then for the overflow, we can set up an irregular section weir. And so if the water level gets up in this rain garden too high, it will pop through this cross section and drop into the storm sewer inlet. And we run it. We run it for, in this case, 20 years. And in our reporting system, we can get monthly averages of any of the constituents. We're showing total suspended solids here. And we can also get annual loads for each year. And it will also depict an average annual load of 81.4 pounds of total suspended solids on average. The total nitrogen is about a little over 3 pounds, and total phosphorus is about 0.44 pounds. And these are reporting products. We can also look at the volumes, the cumulative volumes over the simulation period. So the inflow to the rain garden was about 15 acre feet. And then we had over 13 acre feet going to the groundwater table. This is what's infiltrating through the rain garden. And then there was only 1.7 acre feet that popped off over the surface outlet and went into the storm sewer system. So this has a removal efficiency of almost 89%. Okay. And that's a volume reduction. That's only 1.7 acre feet over the 20-year simulation period moved its way downstream. So a question that comes to mind here is, do we really have to do a 20-year simulation? If you do, you're getting a better average. But if you're trying to go through these quickly, you could probably get away with using a typical and average annual rainfall year. And I just did a comparison, the full 20-year period. We have suspended solids, 88.7% removal. And then for 4 typical years, you can see it's pretty close to that, somewhere right around 90% removal efficiency. This is an exceedance probability chart, something else that we can get as a report product. This tells us that the discharge for this system, meaning the percentage of time that it's up above the overflow elevation, is less than 1%. So we're trapping a lot of the runoff in this small rain garden and perking it out of the system. So let me go to the pervious pavers and talk about those for a little bit. These are located, remember this was a 4-lane road, so they took out pavement here and replaced it with pervious pavers, and then there's underground storage below that. And the model setup would be similar to the rain garden. We would have a node that represents not only the pervious pavers, but the storage below it. We would have a perk link, just like we did for the rain garden. We have a catchment area, which is a manual basin. And then we have a weir link where this could pop off. And if this fills up here, it would pop off and go into a rain garden. So for this example, for the time being, we're going to ignore that rain garden and just assume it pops off and disappears. Here's the storage below the pavers. And again, I got this from Chastain Skillman. This is part of their construction plans. So we made some assumptions. The paver porosity, we assume there's only about 10% void space in there. In the stone, we assumed a 40% porosity. We came up with an average width on it and then a depth of 3 feet. And from that, we were able to develop a stage area and also a stage storage relationship. And on this one, the overflow is also at 160.8, but we have over 3,300 cubic feet of storage, and that translates to over 5 inches of storage. So there's quite a bit of storage in this. This should be very, very efficient in terms of removal efficiencies. So we go back to the perk link again. I won't go into all the details on this, but I do want to make one point. With the perk link, if you select the user specified option for the surface area, you give it a bottom elevation, and then you give it a wetted surface area in acres. This should be the actual area of the soil directly below the bottom of the stone, okay, because that's where all the water is going to perk. You don't have to make a correction on this for the porosity of the stone. We run through the calculations, and we're getting 85 pounds of TSS on average annually. The removal efficiency on this, though, is almost 100%. It's 99.9%. Almost everything is perking into the ground. I think there was maybe one storm event where it filled up and popped off. So very, very efficient. So now let's start putting the pieces together on this system. How would we do that? Well, we have in this little segment of the roadway, we have these various rain gardens. And then we also have pervious pavers in there. And we also have a storm sewer trunk line. And then we have weir links where if one of the rain gardens or the pervious pavers, the storage fills up, we know how it would pop off. And in some cases, it would pop off and go into the storm sewer system and then get carried downstream. And so this would be like a typical ICPR model. You just set up your nodes, your links, your basins, and connect them together. Same way with we add the perk links to these as well to account for the infiltration. So let's take a look at how the removal efficiency works as we move from upstream, which is over on the east side, to downstream on the west side. So we have all these individual rain gardens, pervious pavers, and then all of this, whatever can't infiltrate into the ground, ends up in the storm sewer system, and then flows into a pond where we get additional percolation out of. And then if the pond gets up too high, it will pop off and enter into the lakes. So starting at the eastern end, we'll look at those first 2 points, and I'm calling these point 1A and 1B. We have a lot of BMPs up in this area that are included in the model. The cumulative runoff up to that point is about 17 acre feet. And the volume arriving at that node after we account for all the infiltration with the perk links and everything is about 10 acre feet. So we have a removal efficiency at that location of 42%. Then we go just a little bit farther downstream to 1B, and that's maybe 20 feet farther down. We end up picking up a large area that's untreated, and that enters into the storm sewer system. And when we do that, the runoff volume almost doubles, but we have more volume getting into the storm sewer system, and our removal efficiency drops down to 21% for this if we're looking at it system-wide. So let's see if we can get some of that back. We go down a couple blocks to location number 2. The cumulative runoff volume here is about 74 acre feet, but only 51 acre feet is arriving at that node. So our removal efficiency increases at that point to 31%. Remember, it was like 42%, and then it dropped to 21%. Now we're moving downstream, taking advantage of these other BMPs along the way, and we're now at a 31% removal efficiency. We go to point 3, a few more blocks downstream. We're picking up new treatment BMPs along the way, but we're also in a few cases picking up some untreated areas. So when we get to point 3, 87 cumulative acre feet of runoff, 61 acre feet arrive there. That means about 26 acre feet has infiltrated through our BMPs, and our removal efficiency has now jumped up to 30%. And then point 4, we're going farther down, more BMPs along the way. At this location, we're up to 33% removal efficiency. And then we drop into the pond. And on this pond, we can plot up an exceedance probability chart, and it looks like this pond pops off 4% of the time. So out of the full 20 years tracking it every hour along the way, 4% of the time the water levels are up high enough to flow over the structure. Otherwise, all the water is either evaporated or infiltrates into the soil column. So looking at it along the full length of the road, we're at 42%, drops down to 21, 31, 30, 33%, and then 34% system-wide for everything flowing through that storm sewer system and whatever pops off to Lake Lennon. And we can't forget about the hydraulics. That's all built into the calculations, and we can do things like this, like a water surface profile through that storm sewer trunk line. And this was just one of the storms. This was late September 2011, and it pops up the storm sewer system at the lower end surcharges a little bit then. So the next thing that I want to talk about, another case study, is interconnected wet detention ponds and how we handle those. And this is just a simple wet detention pond. It's out in my office complex here. And these are Harvey Harper's removal efficiencies for wet detention systems. The removal efficiency depends on the detention pond, the detention time in the permanent pool. But you can see that for total phosphorus, it's very efficient in the earlier or for the lower detention times, but then it starts moving asymptotically beyond that point. In other words, you don't gain a whole lot by increasing the detention time a lot. Same with nitrogen. Nitrogen's actually a little bit worse. It comes up very quickly, very efficiently, and then just flattens out. So anyways, these removal efficiencies, we need to apply these to the wet detention systems. So I'm going to show you a case where we have cascading wet detention ponds, and there's 6 of them in this line here. And there are control structures between each of them, and they're all controlled at different elevations. So we get runoff from the drainage area. It goes into the pond. There's some removal that gets associated with that pond that depends on the detention time of it. That pops off, goes into another pond, but then we're picking up another drainage area here, and that pops off, and we pick up another drainage area there, and so on. So how do we handle that? We have the cascading effect here where we're popping off. You can see these are controlled at different elevations. We can apply a removal efficiency to, for example, A-01. Let's just throw a number out there. So let's say it's 50% removal for phosphorus. That means 50% is going into the next one. There might be some additional benefit here, but then we're getting runoff in from the second basin. So how do we reconcile the water that's coming out of A1 and not take another 50% out, but get the full 50% or more or less from A02 and so on as you cascade down? So the first thing that we do is we calculate the detention ponds for all of these wet systems. And the detention time is the permanent pool volume divided by the average annual runoff volume, and then multiply it by 365 days per year. So these vary. A01 has a 19-day detention time, A02, 52-day, and so on. Then we have one pond here that has very little drainage area, but is a big pond that's mostly used for floodplain protection. So that has over 3,000 days of detention. And then if you go to Harvey Harper's removal efficiency curves, you can set those for total phosphorus and total nitrogen based on the detention time. So then we get into the details here. So let's start upstream. We have this basin here represented by this symbol, catchment area, with its distributed hydrology and its EMCs, produces runoff with a certain amount of pollutants that go into this wet detention system. this wet detention system from that table has about a 19-day detention time at the permanent pool level. And so the corresponding removal efficiencies are 60.7% for TP, 34.7% for TN. And we would apply that to that node. So any load that's going into this would be removed at these efficiencies before being discharged through the link. Okay, so that's the first one. That's pretty simple. The problem is the water that has been cleaned up, shall we say, here, ends up in this one. If we apply similar removal efficiencies to that pond, it's going to remove it not only for the runoff, but also for the discharge coming from the upstream pond, which would not be appropriate. Although there is a little bit more removal efficiency for anything coming out of this pond into the next one, it's pretty small compared to the first removal efficiency. So one way that we can do this is we set up I'm going to call it a ghost node up here, not really part of the hydraulics. We assign the catchment area, the basin, to that node. Then we connect that node to the actual wet detention pond with a rating curve link, and we set up the rating curve link so that inflow equals outflow. So we're taking the runoff from the basin and just passing it through this node and this link directly into the pond, but we can assign the removal efficiency at this link. And that's where we can take credit for the detention time in here without over treating the runoff from the upstream basin. And then we just kind of repeat that down this string of ponds. So once we're done, we can do an aggregate report that combines an aggregate runoff report for the 6 basins, the 6 catchment areas, A01 through A06. We can get a monthly average over the simulation period. We can also look at each year of the simulation. I think we did 10 years here. So the average annual total nitrogen from the basins is 1,300 pounds approximately. So now if we compare the annual runoff loads, the aggregate for the 6 basins, and look at how much of each constituent actually discharged out of A06, the last pond, we go from 1,300 pounds of total nitrogen of runoff to 820 pounds that's discharged out of the last pond. And that's almost a 37% removal efficiency for nitrogen. And then for TP, we have a runoff load of 230 pounds, but only 85 pounds is being released to the receiving water body. And so that's a 63% removal efficiency. So you could look at this and then say, okay, if my targets are higher than this, if I need to get 50% or 55% TN removal, maybe we add something at that last pond A06, maybe some type of bold and gold filtration media or something like that to help denitrify it. And then let me show you one other one here. In this case, we have nodes with storage in them, but they're connected by pipes rather than control structures. And by control structure, I mean a weir that's holding water back. So we have, excuse me, B1 connected to B2 with a pipe, B2 to B3 with a pipe, and then B3 to B4 with a drop structure or control structure. B4 is connected to B5 with a pipe, B5 to the channel with a drop structure. So what we can do is we can combine B1, B2, and B3 and treat that as a single pond because they have equalizer pipes between them. And we can combine B4 and B5 together. And then we look at the total permanent pool storage at the structure, calculate the detention time, and then pick off the removal efficiencies. And in this case, we assign the removal efficiency to this node, B3. And then we set up our ghost nodes for B4 and B5, connect them with the inflow outflow rating curve link, and then set the removal efficiencies equal to 81% and about 44% for total nitrogen. And then once we do that, we can quantify the removal efficiencies. Excuse me, I just had to get a quick drink of water. The total nitrogen is about 41%, total phosphorus is about 72% for this system. So in summary, the water quality module is based on EMCs. We can set initial, irreducible, and boundary condition concentrations. The water quality is fully integrated with the hydraulics. Perk and groundwater mounting are built into it, and we can set removal efficiencies at basins, nodes, and links. We went through a screening application where we used a combination of rain gardens, pervious pavers, rain barrels, dry retention. And just looking at that system wide for the city of Auburndale with that mixture that we had contrived, we can get 60 to 68% removal efficiencies. And the removal efficiency depends on the recovery times. How long does it take to recover the storage? If we can recover it quicker, we get the higher removal efficiency. If it takes 3 days, then we would get the lower removal efficiency. And then we went through the gray to green case study, PK Avenue. The volume reductions were via percolation and some evapotranspiration. The rain garden for a single rain garden had 0.44 inches of storage. That was almost an 89% removal efficiency. The pervious pavers and parking with underground storage was almost 100% removal. And then when we put the whole system together, including some areas that had no treatment, we get an overall system-wide removal efficiency of 34%. That would be for total nitrogen, total phosphorus, total suspended solids, because it's a removal of volume from the system. And then I showed you some interconnected wet detention ponds. The removal efficiencies for a wet pond depends on the detention time in the permanent pool. And when you have interconnected ponds, you have to make some adjustments for that. And we looked at cascading wet detention ponds, and that 6-pond series resulted in about 37% removal of nitrogen and 63% removal of phosphorus. And then there are some cases where we can lump ponds together, and this was in the B series. In that case, the total nitrogen was 41% and TP was 72%. And that concludes my presentation. I think that gives us plenty of time for Q&A.
All right, thanks, Pete. Yeah, so as Pete said, we have plenty of time for a question and answer session. I saw, Eban, that you already got to a few via text, but we'll start up with the one that's open right now, where Laura asks, how is sediment accumulation in the rain gardens managed?
With any of these, you have to maintain them. You can't just ignore them. The rain gardens, I went out there a couple of months ago, and they had been in the ground for at least 5 years, and they were looking pretty good. The pervious pavers, and that's not really my expertise, doing them, working on the maintenance and all, but they look like they could use some vacuuming and some type of maintenance on them. But it was in the rainy season and everything was dry except for the pond at the downstream-most end that had a little bit of water in the bottom, which our simulations indicated that should happen. The water table's a little bit higher down there. So yeah, these are designed really well. And I did not see any sediment accumulation in the rain gardens. Anything that was obvious. There might have been some in the rock, but it looked pretty good to me.
Yeah, I would just add that, to your point about maintenance, that goes for all types of GSI or BMPs, that there's an assumption built in that any sediment will be removed on a regular basis. And with permeable pavements, as they accumulate sediment, the infiltration rate will over time reduce or decline, but it starts out really high. And so even if there's a little bit of accumulation of sediment on the surface, they can still function pretty well. The concern is when it, I guess, accumulates too much sediment, it almost kind of it makes it even harder to remove it whenever you do perform maintenance. So it's good to make sure that that's done generally without knowing specifics about different types of permeable pavement systems. We'll usually recommend at least trying to vacuum that out about once a year. That'll vary by application, setting, et cetera.
Awesome, thank you. And I'd also just like to mention we do have a webinar on bioretention in rain gardens, so you can find some more information on maintenance in that. Again, that's on the Florida Friendly Landscaping website. No more open right now, so we can give a few more minutes to see if any other questions roll in. In the meantime, maybe we'll bounce back to one of the ones that you answered through text, Dr. Bean. So we had Diane who asked, some of the wet detention areas looked like they had some erosion on the outside edges. Would they be improved if they used living shorelines or littoral plantings?
Is that a question for Eban?
Yeah, that was
okay.
Well, it was kind of
whoever wants it, yeah.
Yeah, it was kind of I tried to answer a little bit there that, including vegetation along that water's edge, oftentimes will dissipate the energy from wave action to kind of prevent, which is common cause of erosion around the water line of stormwater ponds. And it might help with improvement of water quality and habitat, but I don't know if you know anything more specific about the pond that you were showing there, Pete, from your office. So
is that the one? Yeah, that one. Yeah, right there. I'm not sure that there's that much erosion around it. When I go out there, I don't see any around here. Where I do see it is at the structure. And I was on the owner's board here, and I had to get somebody in to grout it because it had undermined, and that was a problem. So I think this could be probably the outfall could be improved. But I do also think that vegetation around the edges would be nice as well. If I'm not mistaken, the lake doctors come out here pretty regularly to control weed control, not along the edges, but just in the pond itself, to maintain it. But yeah, that structure, just the way they have this T coming out, it's just PVC and it's just kind of hanging there and just and
not supported.
Yeah, right. So I wouldn't like to do things like that. I like to put like a UN wall with a structure and then put kind of a PVC T in with a cap, clean out cap on the top, and then make the T bigger than you need, but then cap the bottom and drill a hole in it. And that serves as a pretty good skimmer. And then
Yeah.
by putting a UN wall underneath it, if you don't do that, if you just put it right above the soil, the velocities are really high and they'll suck the sediment from the bottom and clog it up. And so the ones I've seen that have been most effective, and when I was designing these, we would use the UN walls, and that's almost fail safe.
Yeah, looking at it a little closer, it does look like that's more just the lack of vegetation than actual maybe erosion around the edge there.
Yeah, I've been out there recently and I'm really not seeing any erosion problems. I think it's just low right now, a little lower than normal.
Yeah, and that can happen too, like when if it's, particularly if it's controlled by the water table, if that goes down a little bit more, you're gonna, your water line is gonna recede and you're gonna have areas that are exposed that are usually underwater.
Mhm.
And so that's gonna show sort of that where the vegetation kind of stops, where you're gonna see where that typical water line is. You can kind of see it at the top of the brown area there. That's probably where that water line generally hangs out.
Right. Yeah, I think it's
Great.
about that elevation where it pops over the weir, and then everything below that just kind of bleeds through there.
Great. Yeah, and Diane just followed up and said the picture shows some light brown areas on the right of the pond. If the mowing is done close, the clippings can get in the pond, defeating the quality of the water. Native planting, which don't need fertilizer or pesticides, would help. All right, so I'm not seeing any other questions coming in. So I think that'll do it for us today. Before we get going, I would just like to mention that if you're looking for any funding regarding green stormwater infrastructure projects, we currently have an open project solicitation with the non-point source program here at DEP, and that can be found on Protecting Florida Together and .gov. I'm sorry. We can drop that link in the chat for y'all. And that proposal will be open through August 31st. So y'all have till the end of the month to get a proposal in to Protecting Florida Together.gov. And on that same website, you can also find information on our water quality improvement grant, which has a pretty broad project criteria. So you might be able to find a project that fits there. I'd also like to thank our speakers today. We learned some great information, so we really appreciate that. And I'd also like to thank all of our attendees for joining us today and making this webinar series a great one. So I just want to pass on a friendly reminder that next month on September 21st, we'll have another webinar, and this one will be focused on municipal and regulatory considerations. So again, there folks can learn about how ordinances, BMAPs, BMP trains, as well as the new stormwater rule relate to GSI practices. So please be sure to join us there. You can find the link to register on the Florida Friendly Landscaping website. And with that, just one more big thank you to everyone, and hope everyone has a great day.
All right. Thank you.
Thanks, everybody.
Thank you.
Have a great week.